Let's continue our investigation of solution sets of linear equations. This time we'll focus on consistent systems with infinitely many solutions. Recall that a system of linear equations is consistent if it has at least one solution and otherwise inconsistent. So in this video we'll be looking at this case right here. Let's look at an example. Consider the system of linear equations x1 plus x2 plus x3 is equal to 1, and the second equation is 2x2 minus 6x3 is equal to 2. If we want to bring that in an augmented matrix form, we select the coefficients of the system, making sure to also write down the right-hand sides, and we get this augmented matrix right here. We can use elementary row operations and transform this matrix into reduced row echelon form. I'm going to skip those steps and we arrive at this matrix right here. Let's check that this matrix is indeed in reduced row echelon form. Rows with all zeros are at the bottom. We don't have such rows in this example. Leftmost non-zero entry of a row equals 1. Those are these two entries right here. Those are the leftmost non-zero entries of the two rows, and both of them equal 1. The leftmost non-zero entry of a row is the only non-zero entry in its column. It's the case here as well. This column doesn't have any other entries other than the 1. The leftmost non-zero entry of a row occurs in a column to the right of the first non-zero entry in the preceding row. Again, that's the case. This one here occurs to the right of this one right there. Here again is the reduced row echelon form of our system. Let's translate that into what it really means in terms of our system of equations. The first row means that x1 plus 0x2 plus 4x3 has to equal 0. And the second equation means that x2 minus 3x3 has to equal 1. It appears that we cannot simply solve for x1, x2, and x3 and come up with one solution. Rather, we appear to be free to choose a value of x3, which then in turn will determine the values of x2 and x1. So let's say x3 is equal to t for some arbitrary value t in r. Then this means that x1 plus 4 times x3, which is t, must be equal to 0, and x2 minus 3 times t must be equal to 1. So what does that mean for x1, x2, and x3? That means x1 must be equal to minus 4t, simply by bringing this 4t to the other side of the equation, and x2 must equal 1 plus 3t, which you see right here, and x3, as you recall, was equal to t. So with x1 being minus 4t, x2 1 plus 3t, and x3 is equal to t, we can separate this out into a vector that contains the parameter t and a vector that does not contain the parameter t. Namely, the vector 0, 1, 0, and the vector minus 4t, 3t, and t. If you add those two vectors up, we end up with the vector minus 4t, 1 plus 3t, and t. Next, I'd like to bring this t outside as a scalar that can go in front of the vector, and that brings me to 0, 1, 0 plus t times negative 4, 3, and 1. This system, therefore, has solutions, and that makes it consistent, and in fact it has infinitely many solutions, since we get one solution for each value of the parameter t. Geometrically, we can visualize what's happening in a consistent system of equations with infinitely many solutions. In this case here, we only had two equations. Each of the equations determines a plane in R3 in this example, and these two planes intersect in a line. That line of intersection is the solution set for the system of equations. Next, we'll look at systems of equations that are inconsistent.